Hello guys, you're welcome to this lesson and today we are discussing empirical and molecular formula. So to start with, let's discuss what a formula is. What's a formula? A formula is a chemical notation that shows the constituent or the composition of a given chemical compound. So we have three major types of chemical formulas, which are the empirical formula, the molecular formula, and the structural formula. But today we're just discussing empirical and molecular formula. We're not talking about structural formula. So let's quickly talk about what the empirical and the molecular formula simply looks like. Now, when we talk about empirical formula, we're talking about a formula that shows the simplified number of atoms contained by a given chemical compound. So we talk about empirical formula, we are talking about a formula that shows simplified number of atoms in a ratio format. So that's empirical formula for you. But molecular formula shows the exact number of atoms contained in a given molecule of a given chemical compound. That's the major difference between them. While the structural formula talks about, shows the way the different atoms of a given chemical compound are joined in a structural manner. So, but today we're just focused on empirical and molecular formula. So let's quickly see a couple of differences between them. So we'll talk about molecular formula, for example. Right here we have molecular formula. Right here we have empirical formula. Empirical formula. And here we have the name of the compound we are discussing. So for example, we're going to be looking at a couple of chemical compounds and we state out about two of them and then we'll talk about the major differences between the molecular formula and empirical formula. So for example, we have C6H12O6. As you can see here, we have 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. So we can break them down. 6 can go in all this numbers of atoms. 6 here 1, 6 here 2, 6 here 1. So here we can have CH2O. So what do we have here? This is glucose. This is a form of sugar. This is glucose here. So this is molecular formula. Now, why is this molecular formula? It's molecular formula because of the fact that it shows all the numbers of atoms present in glucose. Glucose has 6 major atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So it's a kind of sugar. But when it comes to empirical formula shows the simplified, it's a simplified formula. It shows the simplified numbers of atoms in ratio 1 to 2 to 1. So here we have, as you can see, we have 1 atom of carbon, 2 atoms of hydrogen, and 1 atom of oxygen. So let's look at benzene. We have 6s, H6. This is the major formula for benzene. 6 atoms of carbon, 6 atoms of hydrogen. So when you simplify it, you have 6N1, 6N1, we just have CH. While this is benzene we are discussing. So we have other examples that we can use to buttress the differences between molecular formula and empirical formula. So what are the major differences? The major differences between them are simply this. Number one, as you can see, molecular formula shows the exact number of atoms present in a given chemical compound, while empirical formula shows the simplified, doesn't show the exact. Now, molecular formula is a standard chemical formula. It's standard, but empirical formula is not standard because we can end up having 2 or more chemical compounds having the same empirical formula after they've been simplified. So that's that. So we're going to be going into calculations very soon. So before we get into calculations, there are certain things you have to know. If you don't know these things, there's no way you need to understand what we're about to take. So before we go directly into empirical and molecular formula calculations, the first thing that we have to know is simply this. We have to know percentage or mass composition alongside relative molecular mass and relative atomic mass. Now we treated this in our previous exposition. So you've not seen some of the past lessons. I would love you to go ahead and see them for you to understand this. So, and also the next thing we're going to be looking at is mole concept. We've not done this actually. So we're going to be doing this, So when we talk about a mole concept is simply, or when we talk about mole, is simply mass over molar mass. Mole is simply mass over molar mass. For example, to say 5 grams of H2O, water, for example, what's the amount of mole in 5 grams of water? So what do we have to do? We've been given the mass of water already as 5 grams. And so all we just have to do is to get the molecular mass. We've worked on how to get molecular mass already. So the molecular mass of H2O, hydrogen is 1 times 2, then oxygen is 1 times 16. Altogether we have 2 plus 16, which is 18. So what's the mole of this? The mole of this is 5 over 18. So just solve that. That's how to get mole. So now, when it comes to empirical formula and molecular formula, it's not a must. You're going to use our mass. Sometimes you could use the percentage, composition, or we call it a percentage composition or mass composition. So these things must be known before we start our calculation. So first of all, percentage or mass composition, and RMM and RAM, and then mole concept. Okay, it's time to look at some work examples. So right here we have the first very question on the board. 3.18 gram of copper 2 oxide was found to contain 2.54 gram of copper and 0.64 gram of oxygen. What is the empirical formula of the compound? Now we've been given all the information we need about this very compound, and so we're asked to write the empirical formula of this very compound. So as you can see, 3.18 gram of copper 2 oxide contains what? What does it contain? It contains 2.54 gram of copper. Copper I see you, copper. And what else does it contain? 0.64 gram of oxygen. So we are asked to write the chemical formula for this. Now, don't forget something. By the time you add those two together, 2.54 gram and 0.64 gram, when you add them together, you will get 3.18 gram of copper 2 oxide. So now how do we write the chemical formula? Don't forget the two things that we need to know. The first is what we'll call the mass or the percentage composition, and after that, the mole concept. So you're going to be using the two of them. For the mole, it's down to the mass of the molar mass. Or sometimes, if you don't want to use the mass, you can use the percentage of each of the mass. Like 2.54 of copper, we have more copper in this than oxygen. You have 2.54 gram of copper in that is out of 3.18 gram of copper 2 oxide, and we have 0.64. So we have more copper than oxygen in this very chemical compound. So now what do we do? The first thing, we're going to draw our table. I'm going to draw our table. This copper here, the copper section, and this is the oxygen section. So for the copper, we have 2.54 gram of copper, and while here we have 0.64 gram of oxygen. Now what we're going to do, we're going to get our mole, the mole for each of them. So what's formula for mole? Mole is mass over molar mass. So mass over molar mass, or you can call it, it depends. You could call it mass over atomic mass. It depends if you just one atom of that very compound we're talking about, like let's say just an atom of copper. So what's the atomic mass of copper? Is 64. So 2.64, 2.5, I beg your pardon, over 64, while oxygen is 0.64 over 16. Now I'm going to show you also that we could use our percentage. We could decide to use percentage. Once we're done with this, we try it the other way around. So 2.54 over 64, there's a mole, the mole of this, and also there's a mole of this. So 2.54 over 64, we're going to be using our calculator to get that done. Let's see what that would give to us. 2.54 divided by 64. What do we have? We have 0.039. So we can call that 0.04 approximately. So while this 0.64 divided by 16 will give us 0.04 also. So we have 0.04 here, 0.0. So you have 0.04 moles of copper, while you also have 0.04 moles of oxygen. So what are we going to do next? Here we have 0.04 mole of copper, 0.04 mole of oxygen. So what we're going to do next is this. We are going to use the least mole to divide all through. So for the fact that we have just two major stocks we're working on here, copper and oxygen, we are going to use, and they are the same, so we're going to use either of them to divide both sides. Well, if you have more than one, if you have like copper, oxygen, and another element, and we have different moles of this very element, what we're going to do is we're going to use the least mole to divide all through. If you use the highest mole, then you're going to be having an issue because you may end up with a 0 point something, on some section, in some sections. So what we're going to do now right now is 0.04. We'll divide all through 0.04. So this divide this, we have 1. This divide this, we have 1. So what do we have right here? We have copper 1, oxygen 1. What was that? Copper 2 oxide. This is an empirical formula for copper 2 oxide. Now, there's another way we could go about this. We could use our percentage composition instead of using the mass composition that we use here. So if we use our percentage composition, as you can see, 3.18 gram of copper 2 oxide contains 2.54 gram of copper and 0.64 gram of oxygen. Now, we could use our percentage composition. Now, how do we do that? We do that by getting the percent of each of this element. Now, 2.54 gram of copper, how much percent of that do we have out of 3.18 gram of copper 2 oxide? We're going to get that. We also get the percent of this oxygen, 0.64 gram of oxygen. So let's see how that will pan out or how that will play out. So this Cu here, this oxygen right here. Now, when we talk about 2.54 gram of copper out of 3.18 gram of copper 2 oxide, what's the percentage of that? So let's see what that is. 2.54 divided by 3.18. Now, right here we have 0. Okay, times 100. Times 100. Right here we have 79.87. So 9.87 is hitting as 80%. Let me call that 80%. So you have 80% copper here. So if you have 80% copper, out of 100%, what we have right here is 20%. So, because sometimes you may not be given the mass of the constituent element. Sometimes you may be given the percentage. So if you're given the percentage, it's the same thing. Just get the mole. Just get the mole of each of them. So this is going to be the mass. This is assumed as the mass. Mass over molar mass, 64. Mass over molar mass, oxygen is as a mole of atomic mass of 16. So this is more or less like saying 80 gram and 20 gram, but it's 80% that represents the mass of this very stuff. So 80 divided by 64, that's the next thing we're going to do. Let's quickly divide. You're going to get the same result. 80 divided by 64, that'll give us 1.25. Now 20 divided by 16, you also give us 1.25. Wow. So what do we do next? The next thing we do, we're going to use one of them to divide all through. Normally we use the least to divide all through, but they are the same. Just take out 1. You see you have copper 1, oxygen 1, which is copper 2 oxide. As simple as that. Okay, here's another example. Let's look at the second example for today. Now we are given the analysis of 2.12 gram of a compound, a chemical compound, gave 0.33 gram of carbon, 1.82 gram of the same compound, gave 1.55 gram of sulfur. Calculate 1. The empirical formula of the compound. 2. The molecular formula of the compound, given its vapor density is 38. Now, how do you solve this? Now, as you can see, this question is quite very tricky, but it's very simple also. The analysis of 2.12 gram of a compound gave 0.33 gram of carbon. That is a sample of that very compound. Now, according to law of definite proportion or constant composition, now this law states that regardless of the method you use in producing a given chemical compound, it does not change the proportion of the elements that make up that very given compound. So we're talking about a given compound. We're not told the compound. We're told that 2.12 gram of that compound contains 0.33 gram of carbon. Now that same chemical compound, 1.82 gram of that same chemical compound contains 1.55 gram of sulfur. So now we're asked to get the empirical formula of the compound. Now it's the same compound, but different quantity of the same compound was used to carry out this activities. So first of all, the best thing we're going to use now is to use percentage, percentage composition, because according to the law of constant composition, it doesn't change. You understand? So if 2.12 gram of the compound gives us 0.33 gram of carbon, so let's say the percentage of carbon in that very compound, that's going to be 0.33 gram over 2.12 times 100 over 1. This is for carbon. You are trying to get the percentage of carbon in that very given compound, so you're going to use our calculator. Let's quickly do that. So 0.33 times 100, then divided by 2.12. What do we have? Then carbon, we have 15.6% carbon. That's what we have. This very compound contains 15.6% carbon. Now, this same compound, another a portion, another volume of the same compound was being picked up. 1.82 gram of the same compound gave us 1.55 gram of sulfur. So let's say the percentage of sulfur in this very compound. So that's let's say 1.55 out of 1.82 that was used times 100 over 1. Let's see, out of 1.82 gram of the same compound, you got 1.55 gram of sulfur. Let's see the percentage of sulfur. 1.55 times 100 divided by 1.82. So you have 85 point, 85.16%. So you could just round this up to 15%. Why this is going to say 85%. So it's balanced, as you can see. 85% sulfur, 15% carbon. So these are the two things we're going to use to get our empirical formula. Okay, the next thing you're going to do now is to get the mole for each of these elements in this compound. So you're going to be doing that using this tabular format. So first carbon, next sulfur. So carbon is 15%, so 15% is more or less like 15 grams. So 15 over what's the atomic mass of carbon is 12. Then sulfur is 85% over what's the atomic mass? 32. Now we're going to get the mole for this. So let's get the mole. So mass over molar mass, mass over molar mass. So let's see that 15 divided by 12. That'll give us 1.25. 1.25, good. So the next there is 85 divided by 32, 2.656. So let's say 2.66. That's 2.66. What do we do next? The next thing we're going to do, we're going to use, this is what you're going to use the least to divide all through. If you use 2.60 to divide all through, you end up with 1, you end up with 0. Something. It doesn't make any sense. So you're advised to use the least, the smallest of them all, 1.25, 1.25. 1.25 divided this is 1. Yeah, 2.66 divided by 1.25. Let's see what we're going to get from there. 2.66 divided by 1.25. That is 2.12. 2.12 is even as 2. So what do we have? We have C1S2, which is CS2. This is our empirical formula. So the next thing we're going to get now is our molecular formula. Now, we are asked to get the molecular formula. We've been given the vapor density. So how do we get the molecular formula? Let's see how we solve for the molecular formula. So the molecular formula is very easy. It's very easy. I just want to show you, I'll just show you the major difference between them. You've seen the difference between them already, but the arithmetic difference between them. That's what we're going to look at. So how do we solve for molecular formula when we have empirical formula already? You have empirical formula. How do you get a molecular formula? Now this, if you don't forget, you have samples like this. Let's say benzene, for example. If you look at benzene is C6H6. This is the molecular formula for benzene. By the time you simplify it, you get empirical formula of CH. So how do we get this? How do we get the molecular formula C6H6 from this empirical formula CH? How do we do that? It's just going to be CH times a given number of atoms that will give us the C6H6. That's how we do it. So the C6H6 here, this is a molecular formula, and we can get the molecular mass easily. You understand? So the CH times something will give us C6H6. So that very atom is what N represents. As simple as that. So for us to get the molecular formula, we just have to multiply this very stuff CS2, which is the empirical formula. We have to multiply with a given unknown atom that will give us the molecular formula. So let's see what we are going to do from there. We've been given the vapor density to be 38. Vapor density is given as 38. Don't forget, very important. Now the vapor density, don't forget what's that? That is CS2 times N to give us the molecular formula. That is, the molecular formula is simply the related molecular mass. Let's see that. When you do this, when you multiply this, you're going to get the molecular formula, but we're going to be using the related molecular mass of the molecular formula. So how do we get related molecular mass? Don't forget in our previous lesson, it's called 2 times vapor density. Now vapor density is given already as 30 or 38. So now let's open up this. Carbon is 12. 12 times 1 is 12. Sulfur is 32. 32 times 2 will give us 64. And got to 2 times vapor density, 2 times 38. 2 times 38 is almost there. 2 times 38. 2 times 38. So what do we have? 12 plus this will give us 76 and equals to 76. Divide both sides by 76. What do we have? Our n is 1. So the molecular formula is CS2 times 1, which is taken as CS2. So we have the same molecular formula as the same empirical formula, as simple as that. Okay guys, let's look at the penultimate example for today. Now right here we have determine the value of X in 0.65 gram, 654 gram, I beg your pardon, of magnesium sulfate with X and crystal of water, XH2O, after strong heating gave a residue of 0.320 gram. Now, how do we solve this? How do we approach this? Now, in our previous lesson on percentage composition, we talked about how to get the percentage composition of waters of crystals. If you've not seen that, that's our advice to go ahead and quickly see that. So now, we've been given the mass of a given chemical compound. We've been given almost the exact chemical compound, but we are asked to get the value of this very stuff, the crystal of water. So this magnesium sulfate with some crystals of water. Now, what happened to it? This very compound was heated and it lost its water after everything. It became anhydrous. So we were left with a residue that was just MgSO4, of 0.320 gram. So what is going to be the value of XH2O? What's going to be the amount of water of crystal? That's what we're going to do. Now, we're going to use empirical formula approach first, then before we use another approach, which is going to be an alternative approach. So now, how do we do this? Now, the first thing, let's see MgSO4 magnesium sulfate. Now, the mass of magnesium sulfate is 0.320. That's the mass of magnesium sulfate. So what's the mass of, let's get the mass of the water of crystal itself, XH2O. Now don't forget, this is the total mass of the whole compound, magnesium sulfate with some water of crystal. There's a whole mass. So after it was heated, we got 3.20 as anhydrous. That's the dry magnesium sulfate. So what's now going to be the mass of the water of crystal that was, that was heated up? So that's going to be 0.654 minus 0.320 this gram. That will give us 0.654 minus this will give us 0.334 gram of the water of crystallization. So quickly, we're going to get the mole for each of them. We're going to get the mole for each of them. So let's get the mole. First of all, the MgSO4 on this side and the XH2O on this side. So first, what we have is 0.320, which is the residue. Now is 0. What do we get there? What do we have here? 0.334 gram of H2O. Now we're going to get the mole. What's the mole? Mole is simply mass over molar mass. So we're going to get the molar mass of MgSO4 and also the molar mass of H2O. Let's get that done right away. So MgSO4, what's the molar mass? 1 atom of magnesium, 1 times 24. 1 atom of sulfur, 1 times 32. 4 atoms of oxygen, 4 times 16. So here is 24 plus 32 plus 4 times 16 is 64. So 24 plus 32 will give us 56. 56 plus this will give us 120 gram per mole. That's that for MgSO4. While for H2O, 2 atoms of hydrogen, 2 times 1. Hydrogen has 1 atomic mass unit. So 1 atom of oxygen, 1 times 16. So it's 2 plus 16, 18 gram per mole. These are the molecular masses. So the first, we're going to be using 120 to divide it. While this, we're going to be using 18 to divide it. So quickly, we're going to be using a calculator to get this done. So let's do that. So first, we have 0.320 divided by 120. So what do we have? We have 0.0.0026666 and so on and so forth. You just approximate that. Then 0.334 divided by 18. Let's see what we've got. 0.0185555. And so now the question is, we have our moles already. Which of them is smaller or is the least? Each of them is lesser than the other means. You're talking about it in two things. So 0.00267, 0.0186. Now, this is surely smaller than that because if you look at them, you look at the two decimal places, 0001. So this is bigger than this. So you're going to be using this to divide all through. 0.00267, 0.00267. This takes out this. What do we have? Let's use our calculator to check that out. 0.0186 divided by 0.00267. We have 6.9666. So this one approximately 7. So what we have here, MgSO4, we have MgSO4, and we have 7 crystals of water. So the 7 crystals of water as simple as ABC. So we're going to be using another method right away. Okay, let's see another way we could solve this, an alternative method. Now, another way we can solve this, you're going to use the percentage composition method. The percentage composition method. So first of all, since we have MgSO4 XH2O, so the first thing you're going to do, you're going to get the absolute relative molecular mass. Let's get the molar mass first. So magnesium is 1 times 24, plus sulfur is 1 times 32, 4 atoms of this, 4 times 16. Then all this together, then plus X here. Hydrogen is 2 atoms, so 2 times 1, hydrogen. Then plus oxygen, 1 atom, 1 times 16. So what do we have? 1 times 24 is 24, plus 1 times 32 is 32, 4 times 16 is 64. Then plus X, 2 times 1 is 2, plus 6, plus 16, and then. So 24 plus this is 56, plus this 120, plus 2 plus this is 18, 18x. So this is the absolute relative molecular mass. There's a mass of all this compound, mass of magnesium sulfate, X crystals of water. So now we are asked to get the value of this crystal of water. We don't know what it is. So what we're going to do now is that we're going to stay focused. Now, if you look at this, this is 18x. So for the crystal of water itself, it's just 18x gram per mole. So how do we now do this? How do we do this? You're going to be using what we call percentage composition, or let's say mass composition. There's no need for percentage. So we're going to say 18x over this 120 plus 18x. Now when we do 18x over this, now let's compare it with what we have here. 0.654 gram of all this after strong heating gave a residue of 0.320 gram of just MgSO4. So MgSO4 is 0.320 gram. So if MgSO4 is 0.320 gram, so it means the XH2O as what? What's the mass of XH2, the amount of water that left? Now we got that already in the previous method. 0.654 minus 0.320 grams. So that's 0.334 grams. So that means what we're talking about, 18x is 0.334 grams divided by the total gram of everything, which is almost the same thing as same thing with 120 plus 18x. So 0.654. That's what we have right here. So what do we do? 18x over 120 plus 18x equals to, so we're going to divide. Let's divide that right away. 0.334 divided by 0.654. That will give us 0.5107. So that's 0.51. So 0.51 we're going to cross multiply. Let's cross multiply. 18x times 1 is 18x equals to 120 plus 18x times 0.51 outside. So quickly, we're going to finish it off from here. We finish off from here. We're going to finish it off from here. So let's finish off from here. So what do we have? 18x here equals to, then 0.51 times 120, 0.51 times 120 will give us 61.2. 61.2. 0.51 times 18, 0.51 times 18 will give us 9.18x. So collect our like terms. 18x minus 9.18x equal to 61.2. So 18 minus 9.18 will give us 8.82. So 8.82x equals to 61.2. Divide both sides by 8.82. 8.82. So we're almost there. We've almost gotten what we want. Using another method, this alternative method. So let's see. So 8.82 takes out the other one. X is 61.2 divided by 8.82. What do we have? Let's punch in our figures. 61.2 divided by 8.82 to give us 6.9 also. 6.9 something. So approximately we have 7 crystals of water. Still the same result, different methods. So it's as simple as that. You're going to be looking at the last worked example. Okay, there's the final example of today's lesson. There's the final example. It's quite a tricky one. Very simple. Now, 0.308 gram of an organic compound contains carbon, hydrogen, and oxygen. On combustion in air, it gives 0.438 gram of carbon dioxide and 0.269 gram of water. If the vapor density of the compound is 62, solve for both the empirical and molecular formula of the compound. Now, this is very simple, but quite a very tricky one. Now, we are given a given organic compound. We are given a given organic compound, but we're not. It wasn't mentioned to us. We're going to solve for that. So they said the organic compound contains carbon, hydrogen, and oxygen. Now, by the time this organic compound gets combusted or gets burned, in oxygen, it gives out 0.438 gram of carbon dioxide and 0.269 gram of water. Now, look at this. Let's say organic compound plus the oxygen. No, after it gets burnt in oxygen, it gives us 0.438 gram of CO2 and 0.269 gram of water. Now, don't forget, when we talk about organic compound, we are talking about, they say the organic compound, according to the question, has carbon, hydrogen, and oxygen. But this time around, the question is quite tricky because of the fact that we are not given the masses or the percentage of each of these materials, each of those elements that make up the very compound. Instead of us to be given each of the masses of the elements, the carbon, hydrogen, and oxygen, rather we are given in a coded form. This stuff was burnt in oxygen, and then we got this, and we got this. We know what this very stuff is made up of. It's made up of carbon, made up of hydrogen, and it's made up of oxygen. So we're now going to get all this, we're going to get the masses of all this from the resultant compound that we got. So organic compound plus oxygen give us this and give us this. So let's simplify this. It's 0.438 gram of carbon dioxide. Do you know what that means? It simply means some measure of this organic compound combines with oxygen to give us this. And this same organic compound, some portion of it combines with oxygen to give us water. So that's what this simply means. So let's look for a way to analyze this. So CO2 first. CO2 naturally, let's get what's the molecular mass of CO2? CO2 naturally has that's one atom of carbon, which is 1 times 12 plus 16 times 2, that is 32. Altogether, an average CO2 has 44 gram. So 44 gram of CO2 contains 12 gram of carbon and 32 gram of O2. That's just a natural phenomenon. By the time you get the CO2, you get the molecular mass of CO2 is 44 gram per mole. So 44 gram of CO2 gives us 12 gram of carbon and 32 gram of oxygen. So now let's do the math. So 44 gram of CO2 equals to 12 gram of carbon. So if 44 gram of CO2 gives us 12 gram of carbon, it means 0.438 gram of CO2 will have how many mass of carbon? Let's see what's going to happen. So let's see, you have S gram of carbon. Let's see how much of carbon we have there. So you're going to cross multiply. 44 times S will give us 44x equals to 0.438 times 12. So divide both sides by 44, all sides by 44. So what do we have? We're going to use our calculator there. 0.438, 0.438, 438 times 12 divided by 44. You have 0.119, which is taken as 0.12 gram of carbon. That means out of 0.438 gram of carbon, out of 0.438 gram of carbon dioxide, we have 0.12 gram of carbon. So if you have 0.12 gram of carbon, what does it mean? It means, let us just subtract 0.438 gram of carbon dioxide. You use it to subtract 0.12 gram of carbon to get the remnant of oxygen. Don't forget that carbon dioxide is made up of 12 gram of carbon and 32 gram of oxygen. So if 44 gram of carbon dioxide naturally contains 12 gram of carbon and 32 gram of oxygen, according to our relative molecular mass, then 0.438 gram of carbon dioxide will contain 0.12 gram of carbon. So if 0.438 gram of carbon dioxide contains this, that means it also contains, let's subtract 0.438 minus 12, it contains 0.318 gram of oxygen. That's what it contains. So by the time you add this together, you get 0.438 gram of carbon dioxide. You can approximate this to 0.32 gram. So we've almost completed the analysis of the zero chemical compound. Don't forget that we are talking about 0.308 gram of organic compound. According to the question, it got burned or combusted to give us 0.438 gram of carbon dioxide and 0.269 gram of water. So we've completed our analysis on carbon dioxide. 0.438 gram of carbon dioxide, will give us 0.12 gram of carbon and 0.32 gram of oxygen. So it's high time we analyze water. 0.269 gram of water, what are we going to get from 0.269 gram of water? So let's see. Naturally, water, H2O, water which is H2O, let's get the relative molecular mass of water. You have two atoms, 2 times 1 plus 1 atom of oxygen, 1 times 16. That is 2 plus 16 will give us 18 gram. So naturally, water is 18 gram. So 18 gram of water will give us 2 gram of this hydrogen gas and 16 gram of oxygen. So if 18 gram of water, 18 gram of water, H2O, gives us this. So let's analyze. 18 gram of H2O of water is equal to 2 gram of hydrogen gas. So what are we talking about? You're talking about 0.269 gram of water. So if 18 gram of water gives us 2 gram of hydrogen, then 0.269 gram of water will give us S gram of hydrogen gas. So what's the next thing we're going to do? The next thing we do now is to cross multiply. 18 times x is 18x equals to 0.269 times 2. So what do we do next? The next thing we do is divide all through both sides by 18. So x is 0.269 times 2 over 18. So we are going to impute our figures into the calculator. 0.269 times 2 over 18 will give us what? That will give us 0.269 times 2 divided by 18. What do we have there? 0.02988. So that will give us 0.03 approximately gram of, that's what we have, gram of hydrogen gas. So it means naturally 18 gram of water contains 2 gram of hydrogen. So if 18 gram of water contains 2 gram of hydrogen, then the 0.269 gram of water will contain 0.03 gram of hydrogen approximately. So now since we've gotten this, now let us get, let us get the amount of oxygen that we have in 0.269 gram of water. So what's the amount of oxygen? That'll be 0.269 minus 0.03. That'll be, let's do that math. So what's that? 0.269 minus 0.03 will give us 0.239. That is 0.03 here, 0.239 gram of oxygen gas, which is approximately 0.24 gram of oxygen. That's what we have. So we are done with this analysis. So we're going to transfer it over there. So the next thing we're going to do now is to draw our table and finish up the whole thing. So right here, this is our analysis for this. 0.269 gram of water contains 0.03 gram of hydrogen, 0.03 gram of hydrogen, and then 0.24 gram, 0.24 gram of the oxygen that we have. So everything is set, and don't forget our vapor density was given as 62. So the next thing we're going to do now is we're going to draw our table and then finish up the whole thing. We're going to get our empirical formula first, then our molecular formula. So quickly, let's do that. Let's draw our table and finish up what we started. So right now we got all our readings, we got all the parameters, everything we need. Everything you need is ready. So don't forget, you're talking about 0.308 gram of organic compound. And don't forget, it was said that the compound was made up of what? Carbon, hydrogen, and oxygen. This compound is made up of carbon, hydrogen, and oxygen, according to the question. So we are very much aware of the amount of carbon we have. We know the amount of hydrogen that we have. But really, we don't really know the amount of oxygen that we have. But we're very much aware of the fact that what we have here is 0.308 gram of the organic compound that we're working on. So if we're working on 0.308 gram of organic compound and we have carbon to be 0.12 gram and hydrogen to be 0.03 gram, so to get the remnant, which is the amount of oxygen, will be very simple. Just add this and this together, then we use this to subtract them. So first of all, our table, that's the carbon, this hydrogen. So the last one is oxygen because this compound was said to be made up of carbon, hydrogen, and oxygen. So for the carbon we have 0.12 gram. We know that. For the oxygen, we have 0.03 gram of oxygen. And for the hydrogen, I beg your pardon. Then for the oxygen, we don't know what the oxygen is. So but we're going to get it right now. So that'll be 0.308 minus the summation of this to 0.308 minus, let's do that quickly, 0.12 plus 0.03 right here. So what do we have? That will be 0.158, approximately 0.16 gram of oxygen. So we have everything we need already. By the time you sum up all this, you end up with about I think 0.31 gram approximately. So we are ready, we're good to go. So the next thing we're going to do now is to get the mole for each of this. We're going to get the mole. So how do we get the mole for carbon? Mass over molar mass. The molar mass is 12. For carbon, hydrogen is 1. Oxygen is 16. So 12 in this will give us 0.01. 1 in this will give us 0.03. 16 in this will give us 0.01. So what do we do next? 0.01 is the least. Don't forget you're going to use the least to divide all through. If you use the biggest mole, you end up with 0. Something. So this 0.01, 0.01, 0.01. So you divide all through. We have 1 here, we have 3 here, we have 1 here. So our empirical formula is C1, H3, and O1. So what do we have? Is CH3O. This is our empirical formula. So let's get our molecular formula after we've gotten our empirical formula. Don't forget that for us to get our molecular formula, what we have to do is to look for an atom. That atom will be a form of unknown. We use the atom to multiply the empirical formula, and that will give us our molecular formula. So what I'm going to do, we write our CH3O out times the imaginary number of atoms or atom, which will give us our molecular formula. But the molecular formula, we're going to get our relative molecular mass. So don't forget our relative molecular mass is 2 times vapor density. We're given the vapor density as 62. So let's get the RMM of these also. Carbon, 1 atom, 1 times 12, then plus 3 atoms of hydrogen, 3 times 1, plus 1 atom of oxygen, 1 times 16, all in brackets, times the number of atoms, imaginary 1, then 2 times vapor density, 2 times 62, right up there. So 1 times 12 is 12, 3 times 1 is 3, 1 times 16 is 16, all in brackets, and equals to 2 times this to give us 124. So 12 plus this is 15, 15 plus 16 is 31, 31 and equals to 124. We'll divide both sides by 31, so n is 4. So the number of imaginary atoms is 4. So let's get our molecular formula. We're good to go now. So it means our molecular formula is CH3O times 4, which will give us C4H12O4 is our molecular formula. As simple as ABC. Okay guys, at this very point in time, it's time for us to get ourselves tested on how much we've gotten from today's lesson. So we have a couple of questions to test ourselves with. So here, the very first one, the analysis of a compound gave this. 1.25 gram of a compound contains 0.62 gram of potassium. 2.51 gram of the same compound contains 0.51 gram of sulfur. 1.87 gram of the compound contains 0.57 gram of oxygen. Solve for the empirical formula and molecular formula if RMM related molecular mass is 158. As simple as that. The next one, solve for X in 0.520 gram of nickel sulfate and X and crystal of water after strong heating leaves a residue of 0.304 gram of the NiSO4. So nickel is 59, sulfur 32, oxygen 16, hydrogen 1 atomic mass unit. So the very last question, an organic compound with a molar mass of 126 gram per mole contains carbon, hydrogen, and sulfur. On analysis, 1.5 gram of the compound produced 2.8 gram, 2.8 gram is 0.363 gram, and 1.1 gram of barium sulfate, water, and carbon 4 oxide. Now, barium sulfate is BaSO4, not barium sulfide, and respectively. Solve for the percentage composition of each of the elements. 2 for the empirical and molecular formula of this very compound. So these questions are very easy. We've worked on them all. So I would love you to solve this and leave your answers in the comment section. So if you found the very lesson resourceful, please subscribe to the very channel and share this very lesson. See you in the next lesson. Thanks.